I'll just get started here. So yeah, we're going to be talking about, it's a one-on-one tutorial, but we're going to be talking about dataset consolidation and comparison at scale using MongoDB, a pretty specific use case that we have at Adobe. Talking mostly from the app layer, but happy to dig into some of the DB innards if we want to and how we're using MongoDB to optimize for this. Questions welcome throughout. Again, kind of one-on-one here, so feel free to raise your hand or interrupt. A little bit about me before we start. I've done volume data processing for over a decade. Previously, I had another analytics service company for 7 to 8 years. Now I'm in Adobe Analytics. People tend to think of Photoshop and stuff like that with Adobe, but we're pretty heavily in the analytics space with a large customer base. Good bit of MySQL and Mongo experience from the app layer and digging pretty deep into the locking mechanisms and DB layer for MySQL. Got some HBase and Dynamo chops, but less so. A lot of that in the last decade. Gone through a wide array of career roles. Started as a Unix guy, worked on JIS apps for humanitarian demining out of Switzerland for a while. Moved through mostly tech lead stuff after that, but then did transition a few years back to be more of an individual contributor, kind of design guy. Write a lot of code. That's what I do at Adobe. So for background on the data that we're dealing with here, we're talking about Adobe Analytics events as kind of the foundation for the analytics workspace for us. It's bread and butter of analytics for Adobe. It's a record of user experiences for our clients. A set of raw key value pairs describing an interaction. They'll come in trillions per month. Many different potential sources, embedded devices, websites, things like that. It's a really basic e-commerce example, transaction data from a browser event, right? Somebody checking out in an e-commerce situation. And kind of just the session data. You can see the user ID there, product SKU there for what they're checking out, some information about their device and things like that. And that would be submitted to Adobe as an event. The data that I deal with are classifications. That's how clients manage their business metadata for analytics. Really a lookup data set to augment an event data set or another type of data set. Think of it like VLOOKUP or a pivot table from Excel, just on a grand scale. Events are generally useless to clients without this business metadata. And joined reporting happens in proprietary backends downstream from us. Think something like Apache Druid, but a lot faster and more feature-rich. We actually gamed out replacing some things with Apache Druid several years back, but it just didn't work for us, wasn't fast enough. So classification record, what we're talking about here is a key and a list of columns with values. Some records might have as many as 200 plus columns. In a record, I'll probably call it a classification key a lot. It's kind of cheap semantics. So it might kind of conflate key and record a little bit. In fact, it's confusing. Dataset schemas for clients are very diverse. Columns will vary. And this classification data is complex, abundant, and used in a lot of different ways. An example would be unique transaction IDs for a system. So they would be dumping a lot of classification data that would essentially look like event data and be joining that with another data set. So I have an example here. You can see the event submission that I had before with a user ID and a product SKU. And internally, the client could import, a lot of classifications for product SKUs that would give us their business structure so they could make reporting sense of this event, right? When you submit an event, you want it to be small and snappy, and then they'll give us the classification data in large bulk downloads. And you can see user ID classifications here. So like they could enter all their user IDs into the system. A couple of columns here, like demography and subscription tier, could be sub-classifications. So the values within those columns could be keys to another classification. So think like a multi-join type of situation for reporting purposes. The consolidation problem that I'm talking about here is that a lot of the client lookup data sets are mapped one-to-one to the event data sets or data sets that they're augmenting. Legacy implementation reasons, we're actually currently finishing up migration to this new Mongo backend. Before that, it was a partitioned MySQL replica set approach. So as I'm saying, I have some diagrams in the next slide, but a lookup data set is paired with the data set it augments. There's often lots of duplication in this approach. You can think of regional sales or product catalogs that are almost entirely or entirely identical for a client. Websites might use the same experience tracking information, and those would have multiple classification data sets. And some of those data sets would have minor additive changes or extra columns, things like that. So this is how it works a lot of times currently, a very naive example. You can see some classification keys along the left side there. And just one value from the classification data set, just to kind of make it simple. So we have 3 classification data sets there, just simple product catalog kind of information. And each of those could be paired up with an event data set for the purpose of reporting. Not really ideal, a lot of duplication in the back end. How it really should work would be that you would have one lookup data set for all of those event data sets, right? This decreases processing and client pain, less fan out imports. We run into the broadcasting problem if you're familiar with it. So this would lead to fewer broadcasts of data downstream. I was talking about our proprietary reporting backends. We're basically doing a fan out broadcast of classification data sets to a lot of consuming servers for high-speed reporting kind of thing. So the broadcast would be larger if you're consolidated, but you would be doing less broadcasts, right? Larger data sets do have some hangups when you get to joins and broadcasts like I was talking about, but that's another talk in and of itself. A lot of work goes into optimizing there. A few quick notes on our environment. We have a distributed worker pool, microservice suite. We're mostly Java code, Spring Data Mongo for DB access, a good Java library for writing Mongo, rabbit queues for sending data around the application. And the DB work for us is mostly done asynchronously, or entirely done asynchronously for this workload that I'm talking about, with idempotent jobs that can replay over and over again with the same result. For Mongo, we have about 200 terabytes of data total spread across 3 different clusters or environments. We actually do have another Mongo database in each environment for the synchronous UI workload, dataset schemas, things like that. Our largest key cluster is 20 shards or 60 nodes, and we're running all this containerized using Kubernetes and Percona. So we manage things ourselves. We're heavily optimized for fast read speeds. I have another talk later on in the conference here, going into a lot of this in more detail. So consolidation of data sets for us at a high level. So to begin with, clients have this list of data sets that they want to combine. So they'll pick them and they'll order them by precedence for handling any conflicts between data, right? Give us a precedence order so that we know if conflicts between keys in different data sets happen, which version of the key should win in the target consolidated data set. We support 2 different conflict strategies right now, a key overwrite strategy and a key union strategy. I'll get into those in some more detail later. Then you generate the consolidation data set. This is basically running through the schemas of your input data sets and their metadata and doing some combinations there to generate your target data set schema. Then you iterate through the data sets that you want to consolidate, copying or merging keys. First data set that we move over is essentially a full copy of the data set to build kind of a template consolidated data set to merge into. And the rest of them run the merging algorithm that I was just talking about. We do some pretty heavy, so in order to understand the results, we do a sanity check comparison for each input data set. So basically do a sampled comparison against the consolidated data set to see how identical they are. We'll get into that in some more detail later. And then clients get a chance to approve and finalize the results. When they finalize, it takes the new data set, which is the replacement for all the consolidation data sets, takes it live for reporting purposes, and we'll keep the input data sets around for a period so they can do comparisons and do rollbacks if they need to. Some notes on the algorithm before I get into it. Column ID remapping complicates matters. This is just some innards, but it basically dictates that we need to do some processing at insert time. I was saying a classification record has a lot of columns. Those columns have a name, but they also have a unique identifier, which has meanings elsewhere in our ecosystem. This remapping is handled at the insert and merge time for any record with a lookup structure that's generated at the beginning of the consolidation, basically taking all the input dataset schemas into account. I played with using aggregation for this, got pieces of it working, but generally I try to avoid the aggregation pipeline in Mongo unless it's being used for something very simple. It gets really hairy. Opted for more functional Java code for readability purposes. It's a lot easier for unfamiliar engineers to understand and also maintainability. Modularized Java code is a lot easier to test, things like that. More parallelization would be possible for the algorithms that I'm talking about here. I could split the merging of records into an individual job per input dataset. But in that case, there's actually some downsides. And we need this to be reasonably fast, but it's kind of a one-time job for a given client set of input data sets. They might run it a few times for those input data sets if they tweak things. But we don't need it to be super lightning fast. We need it to be reasonably fast. That being said, parallelizing within an individual consolidation is useful. We have very beefy worker nodes. And just to highlight it again, data sets are ordered by precedence when it comes to conflict resolution. Some complex pieces are left out of the pseudocode that I'm going to get into in a little bit. So we run as jobs alongside other migration and client load. So we have a distributed worker pool, like I mentioned early on. At that level, we handle a lot of work in progress limiting for clients, throttling if people are hitting the system too hard. This is an asynchronous load for importing data, as I was saying. Doing scaling horizontally if we need to. We can do auto scaling and a lot of monitoring. Most of our monitoring for jobs is around percentile numbers for job latency and throughput, and queue sizes if queues start backing up. We do a lot of progress tracking at the job layer tied to a lot of retry logic, so pick up where we left off in case of errors. Networking issues do happen a lot, things like that. Column ID remapping, as I said, uses a lookup structure that gets passed around. And column merging is functional comparison and union code. Works very similar to how you might think, but don't show it really. Complex doesn't mean this stuff is interesting. It's mostly omitted going forward. For our access patterns, don't know if you're familiar with clustered Mongo, but our shard key is 4 bytes of the classification key hash. So in my example, if a client was importing a bunch of user IDs into a data set, those user IDs would be hashed to generate our shard key. It gives us a good distribution across our entire cluster. The shard key is in all the queries that I'll show for good index coverage and shard routing. We're range sharded, but we do use a hash for our shard key. Just ensures good cardinality and distribution. Happy to talk about it a little bit later. We'll go into a lot of this in my other talk, but happy to discuss it more. We're making Mongo queries using a Spring Data library. So that gives us a lot of streamable result sets, things like that. I also tend to think functionally when I'm writing code. I have some Clojure background. But yeah, again, internal parallelization in a job is useful due to large batch sizes, some pretty beefy worker nodes. You do get diminishing returns parallelizing with small batches and easy workloads. So for some of this, sequential streams could be faster, but I just have some more benchmarking to do. We're actually in early days for this stuff. So algorithm time. So the key override methodology, one of the 2 conflict handling strategies for consolidating data sets. This is really the common client requirement. It's what almost all of our clients want, greater than 90%. I was actually surprised by this. I expected more people to be interested in the key merge approach. I think a lot of it's due to the simplicity of the results that they'll get and just the use cases that they have. This will do very basic unions of data sets. So essentially, each data set has a list of classification keys and combine them all together into the target data set. Again, use the highest precedence version of a key and use that key's values as a whole in the target data set. So no record merging. So yeah, when copying a data set, stream through all the records and inspect the keys. This becomes really simple. You don't actually even have to do value inspection to do consolidation because we're really just looking at key existence in the target data set. So if you think about it, if you iterate through the data sets and precedence from most important to least important, just copying keys and checking if they exist in the target, you handle precedence very naturally. And again, remap column IDs as we insert, which does complicate things a little bit. Getting into a little bit of pseudocode here. So yeah, first stream to the records in the input data set. This is kind of the innards of what the query would look like. You can see here we're including the shard key hash in the query, but we're actually using a constant just to hit an index because we're indexed for lookups based off of shard key and dataset ID. If you think about how clustered Mongo works, you want to make queries by shard key. That's actually the index that we use for sharding within Mongo. I can talk about that a little bit more if you're at all interested. And we just need to basically use a greater than a constant to ensure that we use that index. This all streams via Java library Spring Data Mongo. And we can split it into batches to do internal processing and parallelization. For each batch, we have a set of records to filter against the target data set. So the records that we actually want to add are going to be the keys that don't exist in our target, right? So get all keys and their hashes for the batch. A pretty simple query against, so this is getting all the keys and their hashes from the target data set. So existing keys in target would be the keys that already live in the target. Again, I need to include the keys in this query. The shard key is a hash of the classification keys, but based off of the way that hashing works, you can have identical shard keys for different classification keys. It happens within our database. That's fine. You just need to include the key for querying. That gets into kind of chunk routing internally in Mongo. Pull out a set of just the classification keys from our result set. And the records that we know we want to add are just a simple filter against that set of classification keys. So I do a transformation here. For each, do this in parallel. We have very large batches, like I was saying. For each record, set the ID. This gets into some of our copy on write approach. Object IDs actually have a lot of meaning for us. By default, object IDs in Mongo have a timestamp component based off of updated at. We leverage this very heavily in our storage. I'll get into that a lot in my other talk. Maybe we'll have some more people there. But maintain a record timestamp and give it a new object ID. And also you need to avoid object ID conflicts. So we could be inserting this record into the same collection alongside of the input data set that it came from. So we need to make sure that it gets a new object ID because object IDs are a unique primary key in Mongo. And then remap column IDs instead of the dataset ID and do a simple insert operation. This doesn't have to handle upserts at all because we always know that every key will be inserted and new for the target data set. The key union methodology, which is kind of the more interesting one. This handles unions of datasets and keys. So combine all the column values for key records from multiple datasets. More of an edge case for our clients, like I was saying, much less frequently asked for, although we have a handful of very large power user clients who are really pushing for this. I expect changes in a lot more configurability as far as merging options going forward, but we're really just getting it in front of them right now. It's more processing intensive and it supports unioning of schemas between different classification data sets. So, classification data set like user ID would have a lot of columns that it's using to augment other data sets. We can actually union non-conforming schemas from different data sets using this approach. Mongo is awesome for that kind of stuff. The initial pull looks the same as from the other methodology, right? Just stream through the records in our input data set. They get the records that already exist in our target and map them by key for quick and easy to understand lookup. Existing keys in target is again just a query by the shard key, the dataset ID, and the list of the keys that we have, and then return them as a map lookup structure for quick and understandable lookups later in the algorithm. Gather the records together, perform merges and column ID remapping. Basically here, what I'm getting into is we have two different options. If a input record exists in our target data set, then we have to merge with the record from the target data set. If it doesn't, then we just do some simple remapping and transformation operations. And then we'll have two batches of records here. We'll have the ones that we need to insert that are new to the consolidated data set and the ones that we need to serve or save because they exist in the target data set and they're being merged. This is kind of the most interesting piece of what we're doing as far as I'm concerned. So we're consolidating all of these input data sets together. Some of these data sets, like our largest data set in Mongo right now is 1 billion records and it's 1/3 of a terabyte. Some of these things will be very large. Again, these data sets are all living alongside each other in one database. So we don't really want to do a full comparison of every record for each input data set, right? This is more of a sanity check. Our clients are coming in telling us that the data sets that they're consolidating are nearly identical. They can also do reviewing of the results on their own and run their own comparisons before they finalize. So what we do is we sample the records that we want to compare from the input data sets and pull their version from the consolidated data set. As I was saying, we could do a full comparison, but clients could be consolidating a lot of records. They're downsized to gathering the similarity data as we go. If you can think about it, you would generate essentially as much data to understand this full similarity as you have in your input data sets based off of our data structure, which is pretty unappealing for a lot of reasons with big data sets. And also our key overwrite methodology uses some tricks to not even bother having to inspect values. So in this step, we also do some error checking. I'll get into a little bit more. We did not use the built-in Mongo sample aggregation pipeline. This isn't because I hate aggregation, although I kind of do. This is because we're more of a systematic sampling approach. So we're actually sampling records distributed along the updated at axis for an input data set to compare. Our storage is heavily optimized for reading in this way, and it also gives clients a very good view of differences along the timeline of an input data set, right? So we split the data set into, so we calculate a sample size for an input data set based off of the data set size and some variables like margin of error, things like that. We skew it towards a high sample size. Then we split an input data set into S windows, where S is the sample size. And then we'll pull a record from each one of those windows in order to do samplings and comparison. So this gives us the ability to generate a very meaningful result report, right? Clients can actually look at it and see where differences were along the updated timeline of the input data set pretty easily. Again, ways that we store data using a copy on write approach really optimized for this, or our collections are actually sorted by updated at with some wrinkles. Mongo does this by default with object ID. We really lean into that and do some kind of interesting things there. Some pseudocode for this, get the count for the input data set. Pretty simple. We also do it for the consolidated data set. And then the count of keys that are in the consolidated data set that are not in this input data set is a simple comparison of those counts. It's a very meaningful thing, right? How much bigger is the consolidated data set than this input? Calculate our sample size for a given input data set. Use a low margin of error and a high confidence level and a 0.5 distribution. I'm using the population proportion formula for sample sizes. So it's a pretty commonly used one when it comes to sampling against data sets. This is also highly parameterizable at this step. We could accept a full comparison if we wanted to, but we don't really do it or plan to do it. Or we could use static sample sizes here if we wanted to also. And split the input data set into consecutive windows and run all the following stuff in parallel. So fetch an input record to sample from our input data set. So generate an index to pull from, basically using some jitter. So, use our window sizes and a little bit of jitter to pull random records from within windows. Use our indexes for that. And then for that given key, do an actual lookup based off of key within the consolidated data set and pull that record as well. And then for each input data set, consolidated data set pair, do a pretty basic comparison and count the mismatching column values, add those up. And if any columns mismatch, then we know that we have a key mismatch here as well. So those are two different meaningful things for client. And then generate a similarity report distributed along the sampled updated at axis of the input data set. And then at the end, we'll have a lot of similarity reports, one for each input data set that we consolidated from. We could parallelize all this, but I didn't. I designed the algorithm out. It's faster, but it's more work. Assign a source index to each input data set by precedence, store which data set a given column value came from within the consolidated record. So we're using Mongo for all of this, so the schema within the consolidated data set is dynamic. So we can add this instrumentation data as we go in the consolidated data set. And then during merging, just check to see if the data set that you're consolidating from is a higher precedence than the value that's already in there. If it is a higher precedence, then do an overwrite. If it isn't, keep the value that's in your consolidated data set. After the fact, run a simple cleanup of your instrumentation data using scripted unset, but the data will be ignored by the rest of our pipeline, so it's not really a big deal. You can do that at your leisure. I might end up implementing this for key merge, but I don't really see a need at this point. Things are generally pretty performant as is. A few plugs, if you're interested. There are 2 more Adobe talks here at Percona. David's going into one for more of a DevOps and infrastructure-oriented stance on our Mongo backend. I have another talk about kind of our app layer and how we handled our migration from a legacy partitioned MySQL approach to storing our data into a very horizontally scalable Mongo cluster that's super performant for reads. Yep. Just for a few teasers, we tested a slew of CRUD implementations pre-migration, basically wrote out all of the possible different ways that we could think of to access our data for reads and writes, and then tested them using a workload handling system that I wrote out. We weren't really sure what would work well. Actually, there were some surprises there when it came to indexing. Some indexes that I thought we would need that we didn't, things like that, and that just slowed things down. And yeah, we write with a specialized approach, copy on write, which really leans into object ID sorting within Mongo in order to arrange records by updated at. Wired Tiger, as you do updates to existing records, will generate gaps on disk as it moves them around, but we just do operational resyncs. So our entire Mongo database is pretty aggressively sorted by updated at and optimized very heavily for date range exports of data, which is one of our big SLA use cases. Now I'll get into that some more. And yeah, and that's it. Any questions? Just you and me? He's another Adobe engineer, so.
I'm on this. Weird.
Yeah. Okay. All right, cool. Yeah, thanks for coming. It made me feel better about this. Have a good one.
Shouldn't do both in here.